All right. Thank you, everyone, for joining me. This is my presentation on effect systems. Now, effect systems are kind of a newer phrase. I think that's been going around a little bit. They've been used to apply or used to describe a number of different systems. But in general, these systems tend to have a pretty similar set of characteristics and tend to be applied to solve a pretty similar problem space. So we're going to be looking at these in some generalities and how they can be applied to production systems and solve problems in production. Now, I will note my bias. I am the author of Cat's Effect, which is one of these effect systems. So a lot of my thinking and my knowledge is certainly biased in that direction. But most of what you see in this presentation is pretty applicable to pretty much every effect system, not just in Scala, but in other languages beyond. So with all of that out of the way, let's get started. So the main archetype of use case that we're going to be looking at today is the sort of scatter-gather problem. Basically, the idea is you have some sort of networked application that receives some external request over a socket. Inside that request is some sort of initial payload, some data that has to be decoded, some values extracted from that, and that in turn leads to subsequent requests to upstream network appliances. Those take a variable amount of time to come back. Maybe they have errors, something of that order of magnitude. And when they come back, you have to bring those responses back together, encode a response, and then write that to the socket, which is then closed. This paradigm basically describes about 90 to 95% of what people do with Scala when it's not data science. And certainly, easily 90% of what goes on in the JVM just in general. So this is just kind of standard microservices stuff. Maybe you're only scattering to one upstream, not multiple upstream. Maybe you're not doing it in parallel. Maybe you're doing it to a ton of things in parallel. Like maybe your format is JSON, maybe it's Proto, but this paradigm is pretty universal. And effect systems are born of this problem space because this is a very, very common problem to have. And they're about making this problem space more efficient, more scalable, more cost effective, and not just in data centers, but also in cloud. So we're going to talk about why that is and why it is that effect systems are sort of uniquely suited to this problem and the sort of things that they have built up around this problem space to not only make this problem space more efficient and better, but also just easier to write, more maintainable, build up an ecosystem. So anytime you're talking about scaling, you have to talk about scarce resources. And resource management is really everything for scaling, right? When you want to have an application that is handling hundreds of thousands of requests per second in, per region, you're really going to have to be very, very resource light on a per request basis, just to make it cost effective, if not, physically possible. So scale is really about this problem space in particular. And when we think about scarce resources, we tend to think about, a couple of ones very specifically right offhand. CPU is usually the one that people think of first. Memory is also a really, really common one. And then there's one that, is also very, very scarce, actually scarcer than those first two, but people don't usually think of, which is file handles. And a lot of the applications we write today are actually secretly bounded by the number of file handles available in the system. There's other resources we could go into, but the one that we're really going to spend most of our time talking about today is one that we don't usually think about, and that is threads. Okay? Threads are a very, very scarce resource. In general, you can really only have a few thousand per JVM. This is very much a soft limit. Like your thrashing is basically going to increase as the thread count rises until eventually your application just kind of grinds to a halt. This is actually one of the very first indications is the GC pauses. Because of the way that the garbage collector works and the way that it interacts with threads, you usually see things sort of start, pause times increasing. And that's usually a pretty good hint that your thread counts are kind of getting out of control. They're also not particularly easy to work with or lightweight to work with in terms of their sort of, management. So when you allocate them, they usually take quite a long time, relatively speaking. There's a lot of work involved in that. And they're just not a thing that you can kind of create and destroy them frequently. And you certainly can't have very many of them running. Now, to be clear, by the way, there's a little bit of a misconception here that I see sometimes, which is people will make the argument that, this kind of thread limitation is really about the JVM. Like, it's because it's a GC root. It's because the JVM is so heavyweight. And that's really not the case. Honestly, threads that are integrated into the kernel, that are sort of kernel level tasks, are very, very slow. They're very, very inefficient mechanisms, pretty much regardless of your language runtime. So you have to be very, very careful of these things regardless of your platform. But the problem is they are also our only mechanism for manipulating CPU affinity. And we'll come back to what this means in just a second, but this actually means they are both a very, very important handle, a very important lever for us to pull. We absolutely cannot get away from them, but they're also terribly inefficient. And when you're talking about scaling up very high, they can't be, in the critical path of any of that. In addition to talking about software level threads, we really have to talk about physical threads as well. Okay, now physical threads are an even more scarce resource. So what I mean by a physical thread in this case is a CPU or some parallel thread of execution where sort of simultaneous instructions may execute simultaneously on the underlying physical hardware. I use this terminology instead of core or CPU because it's important to differentiate these things when concepts like hyperthreading are involved. For example, the computer to my left, it has, I think it's going to be, sort of 16 CPUs, but something like 20, 22, 20, I don't know, I can't multiply. It's got more physical threads. It starts getting really, really weird when you have sort of big little architectures and things like that, but it has more physical threads than it has CPUs, and really the physical thread is actually the interesting thing here. Now, ideally, each software thread would map down directly to a single CPU, a single physical thread forever. That would be the ideal configuration. We'll talk a little bit about why that is the case. And ultimately, a lot of that comes down to the fact that page faults are very, very expensive. Page faults happen when you have multiple threads contending for a single physical thread. They end up jostling on each other, and that results in a lot of overhead. And in fact, in some applications, I've seen this be as much as 30% of the total runtime in a production application. People don't talk about this very much because context switch penalties and page faults are actually pretty difficult to measure. A lot of our measuring tools actually ignore them. But if you look at things like real time versus CPU time, you can kind of get a feel for what's going on. And really, these can be a very, very, very expensive source of inefficiency. So we want to avoid this. We want to avoid this at all costs, particularly when we're in these very, very high scale sort of settings. One of the ways that we do that is aligning the thread counts and making sure that our unit of abstraction in application space for sequential computation is aligned with the actual hardware unit for sequential computation. Now, intuitively, the reason that this is so important basically comes down to the way that kernels handle threads, okay? So the way that this stuff works is if you imagine you have two separate processors here, okay? So forget about hyperthreading for a second. You have two completely independent processors, and those processors have their own cache hierarchies. You've got your L1, L2, L3 cache, and then main memory sits underneath all of this. When we program an application space, we usually think about accessing data in main memory, but realistically, pretty much anytime we touch data, it's going to be in a cache, and then it gets pulled into the registers on the processor itself. So when a thread is active, you've got the actual code part of the thread that's running on the processor, and the processor is sort of executing through that. And then there's some working sets, some memory that is frequently accessed by the thread, that will be accessed in the future by the thread, which is generally pulled into the L1 and L2 cache, L3 as well, but we're kind of not talking about that here. Now, every processor's caches are essentially independent. There's, again, some wiggle room in the L3 cache, but if you just think about L1 and L2, this holds true. And so when you have two separate application threads that are mapped down to two completely independent physical threads, those threads can have their own little memory working sets. They're pulled into the caches and they can sort of constantly talk to them. And this is very, very efficient because going to the main memory is much, much slower than going to the cache. So this kind of keeps things very, very close together. The problem in this diagram that we're about to see is what happens when you have other threads that are hanging out waiting for time on those CPUs. And in this case right here, we have thread 2, thread 3, and thread 5. And those threads are just sort of sitting there waiting to execute. So when this happens, thread 2 and thread 3 and thread 4, or thread 5, when they need to get time on the CPU, what the kernel has to do is it has to swap them in. And in order to do that, it has to first remove the data that was being accessed by thread 1, and then change the code pointer, change the programmatic pointer to whatever thread it's moving in, which then will in turn result in pulling that data into memory. Now this process is quite expensive because again, we have to go to main memory, pull it into the cache. It's a very long round trip. And the more you do this, the more expensive it becomes over time because you can't really amortize it. So really, the ideal situation is if we didn't have 5 threads here, ideally we would just have 2 threads. And having 2 threads would mean that they would sit on the processor for quite a long period of time, and those things would basically behave just fine. Now, this type of model is great, okay? So in theory, 8 CPUs, 8 threads, go to town. The problem is that threads are also, in the application space, usually our unit of parallelism. And so this is where you get this really unfortunate mismatch because we want to build these types of network applications that run with an enormous number of parallel things. So if you have something like a 10,000 RPS target, 50 millisecond response time, that means you need to be able to have at any point in time roughly 500 concurrent connections. That means 500 units of sequential parallelism independently running within your application space. That's great, but we can't have that many threads, okay? Not only does it cause problems with the GC, but it also causes problems with page faults, it causes problems with the kernel, loads of things go wrong when you start having that many threads. So we can't have one connection per thread. What we really want to do is we want to multiplex our connections across a smaller set of threads. So we have, say 8 threads, we want to handle 500 concurrent connections, so you have a 500 to 8 mapping on things. This is really the observation that at scale, regardless of how you implement it, regardless of what framework you're working within, all systems are MN schedulers, and we'll come back to what that means. So the technique that we have settled on to solve this problem, to actually solve this sort of multiplexing problem of connections across threads and processors is asynchronous I/O, okay? And you can kind of motivate it by starting from input stream. So think about the input stream API, okay? And, input stream is basically just, a relatively simple interface that has a read function that returns an int, or, if you're using some of the other ones, maybe an array of bytes. Now the problem is read promises to return its data to you. Okay, so when you call read, you're going to get the data back or you're going to get an I/O exception. Nothing kind of in between. There's no, maybe call me back later. So that in turn means that the calling thread, whoever's running read, has to just sit there and wait and do absolutely nothing else until the read either returns or errors. And that means it has to block. Okay. Now, blocking a thread wastes one of these very, very scarce resources, right? We just finished arguing that we can't have a zillion threads. But then the problem is, if we're reading from an input stream, which could be a file or could be one of these sockets, we're sort of stuck. And that means that there's no real way to do that sort of map your 500 connections down to 8 underlying threads. If all 8 of those threads are just blocking on one connection socket at a time, you literally can't do this. And this gets particularly bad in scatter-gather workflows where each of those 500 connections results in more upstream connections. So you really have a lot of I/O going on all at the same time. Now, the solution to this, and this is what leads us to asynchronous I/O as we understand it today, are event loops. Okay. Now, in an event loop, you basically have one thread which is talking to the kernel using its I/O APIs, and it pulls the kernel for all outstanding I/O events across all possible sockets or whatever else is going on. So it means that reading and writing is simply a matter of registering interest with the kernel. So you tell the kernel, I'm interested in these types of events. The kernel is going to sort of make that available to you when you pull. Results are then produced back to your individual sequential processes using a callback rather than a return. So we'll go over an example of how this works in a second, but basically the read API, as it is exposed to users in input stream, just doesn't work. So we need a different API, one that uses a callback. And this in turn means that the actual threads in application space are free to work on other connections while they're waiting results for the first connection. And this is really how you can start to spin the flywheel on scale. So in code, the transformation looks a little bit like this. We have a foo function here, and that foo function returns an int, and we can call it by sort of just calling it like a normal function and assigning the result to x. This is very similar to like, input stream read. And, the thread that is actually doing the calling when we assign to the val is sort of stuck waiting for foo until foo returns. And the transformation that we have to apply in order to take advantage of asynchronous I/O and sort of this multiplex scheduling is we basically have to rewrite this type of code into the following. So now foo, instead of returning an int, it takes a function from int to unit and it returns a unit. And then when it's ready with its result, 42, instead of returning that result, it calls its callback. So meanwhile, when we call foo, we pass that callback, and instead of assigning x to a val, we actually just get x as a parameter. This is a much, much more efficient way of going about the problem space, and it solves the problem quite a bit, but it creates other issues in the process. So what this paradigm shift gives us is it moves us from a world in which we are strictly sequential, where like you run foo, then you run bar, then you run baz, to a paradigm in which we are semantically sequential, right? Like we're not actually running things strictly in sequence on the same processor, one after another, after another, after another. Instead, we simply represent, we want to run foo, and then whenever foo finishes, which might be a long time in the future, we're going to run bar. And in the meantime, until foo finishes, we might go off and do other things and like interleave stuff in the middle. But this is what you want from multiplexing, right? That paradigm shift, that's very, very powerful. Callbacks in this case, in code, A happens after B, right? So if you put your call to bar inside the callback for your call to foo, bar definitely won't happen before foo finishes. But you're doing this without the throw and return sort of dance, right? And you're doing it without blocking threads. Problem though, most programs involve a lot of sequential steps. Like it's not like we're just doing two things and then, everything else is just kind of happening in some sort of weird parallel soup. Like we generally think about our programs as A, then B, then C, then D for a good reason. And maybe it's A, then B, then C, then D for every single connection all at once. But like within a connection, it's probably like one at a time. So the issue then is if you do everything using callbacks, you end up with what Node.js developers affectionately refer to as callback hell, which is just like this nested mess of terrible. It's very difficult to work with this. Now, we as an industry kind of realized that this was going to be pretty much unmaintainable some time ago. And that led to a number of changes in major programming languages, most notably JavaScript, Scala, a number of other ones, to try to solve this problem. And I think that was really the first step towards what has now evolved into effect systems. So what we started to feel our way towards were fibers, okay? Now, we generally think of these, or we were usually taught these, in terms of promise or future, okay? So the concept here is pretty simple. A future, or a promise, is really just a callback that has not yet been completed. It forms a monad which means that we can flatten out our sequences. This is like the really, really powerful thing that Future gives us. So rather than having these sort of nested callbacks that you see the pattern from before, where we have a flat map inside of a flat map, which is also inside of a flat map, instead we can just flatten it out. We can say like flat map and then finish that flat map and then do another flat map after that. This is very familiar to anyone who's used Future. It's very familiar to anyone who's used Promise, but this is all that monads are. Monads give us this property right here. So this is super nice because it means no more callback hell. Instead of having that crazy sort of nested thing that keeps sort of like, filling out to the right, now we can have something more like this. Every language has a little bit of a different way of approaching this. This is Scala's. And here we're just basically saying do foo, and then when foo is done and gives us a result in x, do bar, using that x, then do baz, then do quux, sort of keep moving on down the chain. So it really flattens the sequentialization the same way that we're used to seeing it in any high-level language with semicolon or something like that. This is great, okay? And obviously this paradigm started taking off a little over a decade ago. It's been very, very successful, but it does have its problems. And part of the problem is that once you have this tool available to you, it kind of starts to eat the whole world. And people have discovered that putting your whole program into Future starts to get a little painful. You run into a lot of really annoying problems that are just inherent to the way that Future is implemented and the fact that it's a very, very thin wrapper around these callbacks. Problem number one, is the Future running or not? Like if someone hands you a Future, does this represent a thing that's actually happening? Or does it represent a thing that will happen? Or like, is it already done? Like, did it finish? Am I like holding on to some actual memory here? What am I looking at? You can't really reason about that sort of thing with Future. It's just not designed for it. So it can be really, really challenging to kind of piece together large parts of your program when you have this very fundamental uncertainty about what is going on in the computation. The other problem you run into is that very simple refactorings can pretty dramatically change the meaning of your code, right? So take this example right here where you have sort of the sequential foo bar baz quux, et cetera, is very tempting to take baz, which doesn't reference x or y, and just pull it out into a separate variable, right? Like this is just refactoring 101, like give names to things. It's much easier to think about it that way. But the problem is, the program on the left is not the same as the program on the right, because the program on the right could start a Future which begins running for baz right away. Meanwhile, foo and bar go off, the baz Future finishes, now you're holding onto that memory, foo and bar are taking a really, really long time. Your program is behaving a little differently now, or maybe baz is touching resources that foo and bar also touch. And so there was kind of a hidden dependency between them. So pulling it out like this might actually break your program. So this is very dangerous. And anyone who's worked with Futures or promises at a large scale and sort of a very large application, you're going to see this issue. And this is kind of like your day-to-day pain. Really what ultimately this comes back to is the fact that Future is not a mechanism for control flow. It's just a way of wrapping up callbacks. And it is very, very successful at wrapping up callbacks. Like it's very good at doing that, but it doesn't give you anything more than that. So it can be very, very difficult to be certain of things that are quite basic. Like this happens before that. Well, are you sure? Like it's really difficult. And you end up like doing by name parameters and like other things like that, try to fake your way around this, but it's just very, very difficult. You also start running into problems with the fact that as a model of computation, as a model of representing sort of larger computations and programs, a single callback is a really, really blunt mechanism. Like you don't have a lot of control over that execution. And this tends to manifest in things like timeouts, okay? So if you want to have a Future that runs up to some timeout, let's say a socket timeout, so you can time out like slow connections or clients that are zombied or something like that, which you do in every single one of these applications, you have to encode that manually. You generally have to have some sort of shared Boolean state or like something or other that just sort of reflects like, okay, now we're going to shut this down and we're going to cancel whatever is going on. Back pressure. Back pressure is a really, really, really interesting problem, and it's a very important problem to solve for these types of systems at scale. we have to do it explicitly. Like we don't have the ability to say, like, don't run this thing until this other thing finishes. Be really, really sure, like free up the resources, like that type of thing. We just can't do that. And it really comes back to the fact that most futures are handles to results that are being computed present tense. Okay, something. If you have a future, it usually means that something is happening. And by the time you have that future, it might be too late for you to do something about the thing that is happening. Like maybe you don't want it to happen, but you don't have any control over that because it's already happening, present tense. Future is really fundamentally a push model. Things happen, the results are sent to you via these callbacks. And that in turn means at a high level that load shedding has to be really, really carefully planned. And this right here is just absolutely the killer thing. So in production, like these very high scale systems, they're not static. It's not like you're sitting here at 10,000 RPS or something like that and doing absolutely nothing else and it never fluctuates. Generally, you have sort of peaks and valleys. You have times where load spikes up as like a whole bunch of connections come in, and you just have to deal with that. Now, we have high level systems like auto scaling and other things like that to go request physical resources from your underlying topology, but that stuff doesn't happen instantaneously. You have to be able to survive and sort of shed that load, maybe return some errors or like punt things off into a queue or otherwise protect the core system long enough for the reinforcements to arrive. And then the sort of overall cluster can self-heal. If you can't do that, then the symptom is whenever a load spike happens, auto-scaling triggers, but it doesn't trigger fast enough and the existing nodes fall over or they become permanently degraded in some way. And that is a very, very bad time. So in order to address these issues and a number of other issues, we have begun over the last several years thinking about the future, like what's beyond future, the future of future, as it were. And really what we've kind of come to is a couple of pretty basic things. So first off, we want all of the benefits of future. Okay, so all the things that future does really well, wrapping up callbacks, giving us sort of sequentialization, we want that. That's good. Future does a really good job at that, but we want more things beyond that. We want deterministic control flow. We want first-class support for cancellation so that timeouts are this thing that work and you don't have to think about it. They just sort of run. As part of that, we want to make sure that we have really first-class resource management. So if something does get canceled, we don't have leaks or other things like that that just sort of fall apart. And we want back pressure by default. Okay, so we want the base state of the system to be safe. If you get this giant load spike, the system will reject connections, reject traffic, sort of slow the traffic down. It won't kill itself in an effort to handle something that it just doesn't have the physical resources to handle. So put another way, we would rather see slow connections or ideally something like a 302 rather than seeing something like an out-of-memory error or an out-of-file handles error, because the latter two are much harder to recover than the former two. Ultimately, if back pressure is the default state of the system, then you get this sort of load shedding for free. Like by default, it's just going to happen for you. You don't have to think about it. And that means your systems in aggregate tend to be very, very self-healing and resilient. Now, this comes with its own set of trade-offs, but in general, this is a really nice place to be. Like you can just kind of like not worry about this stuff. And all of these things kind of go together. Finally, back pressure by default gives you incremental memory management, like sort of by definition. So that sort of situation where we had earlier where we moved Baz out and Baz was computing something and then we held onto that memory for a long time, not really a big deal anymore. So as you can see in this example here, right, this is the same example that we had earlier from Future, except now we're doing it in terms of I/O, which is sort of the name we tend to choose for these more evolved futures. And in this case, this program is the same as what it would be if we didn't have that val, and instead Baz were inside of the for comprehension. Like Baz is not running until we hit that flat map that sort of sets it off. We're not holding on to any memory, and if foo and bar take a really long time and are timed out, we don't have to go and clean up resources or anything like that. It's just going to get handled for us. So this is a really, really powerful place to be. It also allows us to write higher level functionality with greater ease. So everybody's favorite example of this is retry, where you want to write a simple function that, like, okay, if this action produces an error, just do it again. Well, this is already quite difficult to do with future, because if you just resequence a future, if you re-flat map it, it doesn't rerun the future. It just gives you the value again. So already it becomes a little harder with future, but IO kind of bottles that up. But you can see this even more clearly when we make this function more complex. So here's a version of retry that's been extended to do exponential backoff, where it's the same type of signature, except now we have this sort of backoff thing. We've got this randomizer, and internally it kind of functions in the same way, where it's able to sort of resequence the IO and kind of do all of this stuff and really manipulate it as a first class thing. And the results of this function are itself an IO. So we can keep composing these things together. We can glue these pieces together into progressively higher and higher and higher level pieces of the programs without really worrying about these sort of tangled dependencies or spooky action at a distance or things like that we had to worry about with future, because the IOs are just there, right? They're not running yet, and we have a lot of control over it. We can reason about what's going on. So here's an example, right? Where we sort of create, or we have an action, make request, and we sort of enrich that action with the ability to retry, but then we want to time it out after 1 second. And we didn't have to write timeout knowledge into our retry function. We didn't have to write timeout knowledge into our make request function. It just all sort of works. And the resources are going to get cleaned up. It's not going to sit on threads any longer than it has to. Everything's going to be very, very reasonable. So this is a very, very powerful paradigm, and much more complex examples than this are possible. We also get resource management. So these things are kind of tied together, right? If you're going to be implementing timeouts, you also have to think about what happens to resources that are open when your action is timed out. And so the solution here tends to be to pull them all together all into one thing. So the idea is define an action which opens and closes a resource, and then marry those actions together so that anytime you open a resource, you are always going to close a resource, no matter what happens, whether you complete normally with a result, or if you time out, or you error, or whatever else is going on. You kind of glue these things together and you package that up as a single unit that can be passed around. We can build this type of abstraction, and it gives us this really powerful thing in application space where we can separate our logic that constructs the resource from how it is used, right? So we can go make a resource, give me a file, right? Give me a socket, and then just have that as a thing. And you can safely touch that resource knowing that when you're done with it, it's just going to get cleaned up. So this removes a lot of coupling in practice, all of the coupling across life cycles, weird things that you have to worry about with try finallys and other stuff like that. All of that goes away. It's literally not a problem anymore because it's all glued together. This eliminates an entire category of bugs, very, very common bugs. And again, it marries together this concept of the system should be safe by default. The system should be self-healing by default. Very, very important. So here's an example of that, right? We have a simple connection function that takes a URI and returns a resource of connection. Now, normally this feels a little weird, you're returning a connection to me. Well, connections are things that need to be managed, but that's fine because we've wrapped it up inside of a resource, and a resource has the knowledge of how to close the connection, as you can see in the way it was constructed. Meanwhile, somewhere else in the code, you can write these programs that call the connect function, and now you've got a connection, and you sort of do your thing, then you sort of do your computation, and then you yield, and you don't have to think about all of the different resources that you touched along the way. You can even compose these things together with sort of higher level utilities like race, right? So here maybe you have two read replicas and you want to race a connection against them. Whichever one wins, you're going to keep that winner. The other one you're going to close, and maybe you'll interrupt it if the connection hasn't finished yet. This just works out of the box, which is really, really magical. These types of things and more things built on top of it are part of the benefit that you can get from this really composable building block, this building block that you can trust, that doesn't have these weird corners and angles and surprises like we had with callbacks and with futures. Really what we're talking about is a small and composable functional surface area. It's a reliable foundation on which to build this really complex functionality that we have at a higher level. So things like retry, streaming, we can build whole web frameworks on top of this, and much, much, much more. And like at every single layer of this composition, things continue to work. So I can have, a whole complex process that like handles a connection and then opens some upstream connections and logs to a file and like does all these other things. And then I can like call .timeout on it. And it just works. Like I didn't have to make that work. It just worked out of the box because you have this compositionality. You can safely layer functionality up and up and up and reason about it locally, like only look at the bits that you're actually working on. So this is very powerful. Like it really frees up your mind in a lot of ways. And really what this represents is the next generation of reactive programming. Okay, so it moves the state of the art significantly beyond callbacks and coroutines and sort of these base level primitives that we've been working with for a really long time. By contrast, things like Project Loom, they obsolete stuff like future and callbacks and things like that, but they don't obsolete these more advanced paradigms like I/O. Okay, so I/O really represents an evolution significantly beyond that. So there's some really good examples of this, but one of them is that Loom doesn't give you a solution for timeouts. It doesn't give you a solution for resources. You're really on your own with that. It also doesn't solve the back pressure problem. So you kind of still have to think about load shedding. You really have to make sure you're very, very careful about that, especially in asynchronous systems where it's so easy to open up and handle a lot of connections all at once. Suddenly you have that problem to deal with. Whereas these more advanced paradigms, these effect systems, don't have that issue anymore. You just don't have to worry about it. Ultimately, a lot of this is about setting the guardrails for safer, more composable applications and libraries. And really, in a sense, it constrains the problem space so that we can build deeper and deeper integration with other things. And to me, I think that's one of the most exciting parts about this. By constraining the problem space down, we're able to kind of understand the program, not just like when we are reading it as users, but also when the application runtime is looking at a program. It's able to understand a little bit more about what it does. And this gives us much more complete insight for optimization purposes, both at runtime and ahead of time, and also allows us to build much higher level tooling that assists us in building complex applications and testing them. So ultimately, it's about this algebraic model, right? Like if you know that you can compose A and B together, A and B have some properties, and the resulting A composed B still has those properties, like that's a very, very powerful foundation to build on. And in practice, we do. So we build things like declarative blocking regions to control starvation cases, right? Where we don't want to have operations that are fundamentally blocking, like file I/O, sitting on top of our small set of threads that have to map down to the underlying physical hardware. We want to shut those off to something else. Well, with declarative blocking, that's really, really easy to do. We can build sort of fiber runtimes that work with these sort of large sequential things and understand that like sequences of actions built inside of I/O are likely to refer to the same data as previous stages of the applications. So keep them all on the same thread if you can, then keep your threads mapped to your physical hardware, meaning that you get all of the benefits of your cache hierarchy and very limited page faults, but even with this extremely sort of complex and advanced asynchronous behavior. In practice, this tends to win you about 1 or 2 orders of magnitude better performance than a conventional single queue disruptor pattern, both due to contention and due to normalizing the thread assignments. We can go even further than this still. So some of the things that we've been working on in Cat's Effect are things like cooperative polling on timers, where rather than having this separate sort of timer mechanism that eats up resources and sort of is running a thread and is polling the system and things like that, instead we can actually integrate it into the runtime for these I/O things. And so every time an I/O runs, because we understand that it has this very small granularity because of how it is constructed, we know that we can squeeze in timers between that without losing any granularity. And every application that is a network application has a zillion timers. So really small improvements in efficiency here add up quite significantly. We can even do things like test control. So test control is this really nifty sort of cat's effect utility, which basically gives you a runtime in which time, like the actual wall clock time, is a synthetic concept. And the runtime, integrates the notion of time together with the notion of parallelism. So you can just run your programs that deal with clock time and test them in a very, very fast and deterministic fashion, basically allowing you to write unit tests for things that you never could have unit tested before. So if you remember that retry function from earlier, where we had that exponential backoff, there's actually a lot of very subtle things in that function, things we would want to test. Well, here is a unit test written in munit, which runs that function. And you'll notice that this test is doing things like, it's an exponential backoff of like a minute, but this test runs in milliseconds because time is a synthetic concept, because we have full control over the runtime. We understand what time is, we understand what parallelism is, we understand the structure of your fibers, and test control exploits all of that knowledge to control the scheduling and give you this very synthetic environment that behaves much, much better for these types of tests. So really, it's not just about making programs faster. It's not just about making them scale better, making them easier to write. It's about making them safer and easier to test, and making a more pleasant experience all around, giving users much better tools for solving problems. At this point, right, effect systems have been around for about 5-7 years, depending on how you count. They've been around for a while. They kind of exist in a number of different runtimes at this point. We've got sort of 2 in Scala, 1 in Rust, and then the Go runtime arguably qualifies for a lot of these criteria. These things have been deployed by some of the largest companies in the world at extremely high scale, right? There's a lot of household name services and applications that are powered by effect systems because they solve this problem and because they do it so efficiently and so well. Now, there are a number of assumptions which have to apply for this to be a good fit for your problem space, right? And the biggest assumption is that the number of I/O allocations is sort of linearly proportional to the amount of actual physical I/O that is going up. And this is just a fancy way of saying your application is I/O bound, right? So if you've got a network application of some sort, it tends to be a really, really good fit because, if you're sitting there waiting for a socket or you're writing to a socket or something like that, that will be many, many orders of magnitude more time than pretty much anything you can do with the CPU. And so that means that in turn that the overhead of allocating these I/O objects, of calling flat map, of sort of creating functions and other things like that, that overhead just kind of doesn't matter because it's just drowned out by many orders of magnitude by, the hundreds of milliseconds it takes for some slow network service to respond. So in these types of scenarios, which again is kind of that scatter-gather paradigm that we talked about at the beginning, this could be a really good fit and it could work extremely well. So the allocation overhead in those scenarios is just sort of demonstrably irrelevant. And this really points to a maxim about the nature of functional programming, and it's in particular the nature of functional programming on the JVM, which is that functional programming in the large makes a lot of sense. Functional programming in the small does not. Where functional programming in the small, you're going to be stuck on sort of really tight loops on bytes or something like that. The overhead of the allocations, the immutability is going to really fight you. Whereas functional programming in the large, at the scale of your application or at the scale of connections and fibers and callbacks and things like that, it's actually fine. The overhead is still there, but it no longer matters because it's so infrequent compared to the operations which do matter in the critical path. So this is a really important rule of thumb to keep in mind, and it has proven to be a really powerful way to design practical production systems. So in conclusion, effect systems in general are, at this point, a very well-motivated evolution beyond future. This is kind of what people should be doing. Project Loom is coming, and it's very interesting, but it really doesn't replace these types of systems. Cat's Effect or Zio are pretty much unaffected by it. What it does replace is future, okay? It replaces callbacks. It doesn't replace I/O because it doesn't solve all of these other problems like back pressure and timeouts and things like that. Effect systems performance is objectively fantastic. And in practice, it tends to be much, much better than, even hand-rolled alternatives. So if you're trying to do this sort of stuff by hand, if you're sort of writing your own sort of event loops or things like that, just stop. It's not going to be as good as what these systems can do for you because of how well optimized they are and because of how their sort of global coherency is able to work. So even with the excess allocations that sort of dominate in micro benchmarks and other things like that, in the aggregate, in a large system, effect systems really, really win. So absolutely, you should be using them at this point. You really should be using them. And the icing on the cake is really that they are foundational for these very large ecosystems, these very powerful ecosystems. And we see this, right? Like the type level ecosystem built on top of Cat's effect is really composable and complex. And there's a lot more layers that can be built on top of it. And you can keep doing that without being on shifting sand because each brick kind of fits together really nicely and you have a good degree of confidence in the overall thing. So, all of that is to say, this is a very exciting field. It's a very exciting time in the field, lots of interesting things going on. And definitely this is how you should be building this class of software. I feel very confident in saying that based on experience doing it at very high scale. So with all of that said, I hope there is some time for questions. Thank you very much.